Welcome everyone. So today we will start with modal mu calculus where we ended yesterday. My goal is to go one more time over the semantics of modal mu calculus very briefly so that we make sure that we understand how fixed points work in modal mu calculus. Then I will give you at least two useful patterns that you can use in your specifications. And I guess when you work on your exercise this afternoon or this morning, then you may come up with some other interesting properties that do not fit these two patterns. Then we can sit together and then cook the right pattern for your property, and then you can use it for the future. Okay. So I think the most essential part actually for today is to work on the exercise, and thereby you can learn these things firsthand and make sure that you do understand how this is going. Okay. So again, we are developing a language for modal formulae in order to reason about systems behavior. And if you remember from yesterday, the two motivations for adding fixed points was that you cannot specify properties such that all computations inevitably reach a state which satisfies phi. And you cannot specify, neither you can specify for some execution phi holds everywhere. These type of properties cannot be specified in HML, in Hennessy-Miller logic. They cannot be specified either in Hennessy-Miller logic with regular expressions. That's why you need fixed points, right? And again, if you remember, this was the language of Hennessy-Miller logic with regular expressions: true, false, negation, conjunction, disjunction, implication. And then here you had a slightly more complex structure for regular expressions over actions. So you could specify a single action, a set of actions, intersection, union, plus was union actually, and a star, right? Inside diamond and box. You remember that, right? And what we add today, and we will talk about that, and this is exactly the syntax of MCRL2, is a variable for fixed points, and then two different fixed point operators. This is called minimal fixed point. So mu x dot phi represents the equation x equals phi, where you're seeking the minimal fixed point for that equation, right? So you're seeking the minimal set of states represented by x that satisfy the equation x is equal to phi. And note that in phi, x may appear as a variable as well, right? At the end of the lecture, I will tell you that this x may also be parameterized with data. So you can do things like counting, for example, push-down type of properties, all very complex properties that can never be specified using things like CTL, LTL, CTL star. You have a full expressive power of modal mu calculus with data to express these things very compactly and very nicely. So once Moshe Vardi, I don't know whether you know Moshe Vardi, he was the president of the ACM for quite some time. No, not the president. He was the editor-in-chief of communications of the ACM and a very influential person. He said, modal mu calculus is the mother of all logics. And modal mu calculus with data is the grandmother of all logics. So you can specify very compact formulae that can capture a lot of complex behavior in a single formula. And I will show you one example in the end, maybe using the board, not the slide. So just to recap, mu x dot phi represents the minimal fixed point to the equation x is equal to phi. And nu x dot phi, nu x dot phi represents the maximal fixed point to the equation x equals to phi, right? And one constraint that we always have, x may only appear under even number of negations. So you cannot have mu x and then one negation and then another nu x and then another negation and then x. An odd number of negations, so 3 times negation or 1 time negation. But that's something by which the fixed point construction should work. If you do not satisfy this, then you may not have a unique fixed point, minimal or maximal. Okay, so maybe I shouldn't have specified this, but if you have the equation x equals to x, that's a valid equation, right? Then it has infinitely many solutions, right? Any set of states satisfies x equals to x, right? If you put x here, you get x back. So any set of states satisfies this equation. But in particular, if you're seeking the minimal fixed point, it's trivially the empty set of states, right? Mu x dot x results in empty set of states. It's false, basically, right? So mu x dot x is logically equivalent to false. Is this clear? And nu x dot x is the maximal set of states that satisfy x equals to x, and that's the set of all states. So nu x dot x is logically equivalent to true. Right? Now, suppose we want to specify a state can be reached where x cannot be executed. Help me to specify that using equations. How would we specify this? A state can be reached where a cannot be executed. First off, how do we write down a cannot be executed? Some volunteers? A cannot be executed. Not diamond A true is a good one. A true, yeah, not diamond A true, or alternatively, box A false, right? Everyone agrees with this? A cannot be executed right now is specified as box A false or not diamond A false, A true, right? Now, we want to say a state can be reached where this formula holds. Okay? So either this formula holds right now, or I can reach a state in the future, so I can take a step in which this formula should hold, right? How do I specify that? So suppose I want to write an equation, then I will translate it into our syntax. So either this holds right now, or something else. And what is that something else? Or I can do something, right, after which x holds. Right? Either this holds right now, or I can do something after which x holds. Right? Everyone agrees with this? Where did I leave my pointer? So I guess this is what I wrote here, right? X is equal to x is equal to box A false, or I can do something after which x holds. You agree? Intuitively, do you think I should put mu here or nu? Am I seeking the maximal fixed point or the minimal fixed point? Okay, so he says maximal fixed point. Maybe someone else thinks minimal. So minimal, we have two different votes. So let's calculate and see which one is which, right? So we take one time the minimal fixed point, another time the maximal fixed point. We calculate it on this example, and then we see which one corresponds to our intuition. Okay. So is this intuitive formula, a state can be reached where A cannot be executed, satisfied on this or not? Let me rephrase my question. Which states in this transition system should satisfy this intuitive formula? S2 satisfies this formula, it's true, because it immediately satisfies the first disjunct, right? It cannot do an error immediately. Which other state?
All of them.
Not really all of them.
Not S1.
Okay, S0 and S2 satisfied, because from S0 I can take an A transition and then I end up in a state which this is satisfied. But from S1, no matter what I do, I stay in the same state. So intuitively, if I calculate the fixed point, the right fixed point here, then I should get back S0 and S2, right? Do you agree? You don't agree? No. Okay, so if I'm at S1, no matter what I do, I stay here, right? So I can never reach a state in which A cannot be executed, right? So S1 should not satisfy this formula, whatever the formula is. I haven't decided that it should be mu or nu, but whatever the formula is, S1 should not satisfy it. S0 should satisfy it because it has an outgoing A transition going to S2, and thereby A cannot be executed afterwards. So S0 does satisfy the intuitive formula. S2 satisfies it immediately because it cannot do an A anyway, right? Okay, so let me calculate both the minimal fixed point and the maximal fixed point and see which one corresponds to our intuition. How do I calculate maximal fixed point? How do I calculate maximal fixed point? Do you remember from yesterday? So suppose I'm interested in the maximal solution to this equation. How should I calculate the maximal fixed point?
The set of S0, S1, S2.
Yeah, so I start with x being the full set of states here. I put it as x, and I see what comes out. If what comes out is the same as what I put in, then that's the maximal fixed point. Otherwise, I iterate a few times. Because this is finite, I only need to iterate a finite number of times, and then I reach a fixed point, right? So from which state I can do something and end up in S0, S1, and S2? From which state I can do something and end up in S0, S1, and S2? So what is the result of this? From which state I can do something and end up in S0, S1, and S2? So it's S0, because from S0 I can do an A and end up in S0, for example, or another A and go to S2. That's fine. S1 is also fine, because if I do an A, I end up in S1. That's in the same set. But S2 is not in the semantics of this formula. Why? Because I cannot do anything to end up in S0, S1, and S2. Right? So the semantics of this formula is the set S0, S1. Everyone agrees? Do you agree? You don't agree? You don't understand? No? Okay. So from which state I can do something and end up in this set? If I'm at S0, I can do, for example, this A, and I end up in S0. S0 is in that set, so that's okay. From S1, I can do an A and end up in S1. S1 in that set, that's okay. From S2, I cannot do anything. So this formula is not satisfied for S2. That's why I get back S0 and S1. Okay. Which state satisfied this formula? Box A false? Box A false. S0. S0 can do many A's. I'm looking for box A false. Box A false says if you can do an A, then you should satisfy false. So you should not be able to do an A, right? So which state satisfy this? S2 only, right? Union of S2 with S0 and S1. S0, S1, S2. I started with S0, S1, S2. I got that back. So this is the maximal fixed point for this equation. And what is the moral of this story? That maximal fixed point is not the intuition, does not satisfy the intuition that a state can be reached where A cannot be executed. Because we discussed that S1 does not satisfy this intuitive formula, right? S1, no matter how it evolves, it can never avoid doing an A. While this formula requires that we should reach a state where A cannot be executed. So, in particular, new x dot A false or true x is not the formula we want to specify. In general, it's a little bit of a too vague and too imprecise statement, but new does not go that well with diamond. So typically, if you want to specify something with new, and you don't mix different fixed point operators, you usually have a box here. Okay? As I said, it's a very vague and very imprecise statement. There are exceptions to it. But typically, if you start with new, you expect x to appear after a box. That's a very usual pattern. Typically, new and diamond are a bit problematic. Not always, but typically they are problematic. Okay? Now, let's calculate the minimal fixed point. So the conclusion was that the maximal fixed point is not what you're looking for here, right? Because it does not satisfy our intuition. So now we want to go for the minimal fixed point. How can I calculate the minimal fixed point? This is dying. How can I calculate the minimal fixed point? We start with the empty set. So from which state I can do something and end up in the empty set? I should be able to do something and then end up in the empty set. That's the empty set, right? That's like writing. That's the first thing we learned about Hennessy-Miller logic. This is equivalent to. This is equivalent to false. This is logically equivalent to false, because either you cannot do something, then this is violated, or you can do something, then you should satisfy false. So this is logically equivalent to false, right? So diamond true empty set is empty set, right? Everyone agrees? If you can do something, then you should end up in empty set. You cannot end up in empty set. So this is empty set. Which states satisfy box A false? We did it in the previous exercise. S2 was the only state that cannot do an A. What is the outcome? S2. We started with the empty set. We ended up with S2. So this is not yet a fixed point. We should iterate again. How do we iterate again? I write it here. Is it visible from the back? Also from that back? No? Yes? So true S2. From which state, if I do something, it's possible to do something and end up in S2. From which state it's possible to do something and end up in S2? What did you say? S0, right? From S0, if you do something, namely if you take this A transition, you end up in S2. So S0 is definitely in the semantics of this formula. Anything else? Any other state that can do something and end up in S2? No, right? There is no other state that can do something and end up in S2. What states satisfy this? We had it already, S2, right? S2 union with S0 is S0 and S2. I started with S0, with S2, I ended up with S0 and S2. So this is not yet a fixed point. I need to iterate once again. Yeah, I started with S2 here. I ended up with S0 and S2. So this is not yet a fixed point to this equation. So I should iterate once more. So I will erase this one. Instead of empty set, I will put here S0 and S2. Which states can do something and end up in S0 and S2? Yeah, S0 can do an A and end up, for example, in S0, which is fine. What else? Is there any other state that can do something and end up in S0 and S2? No, right? So the semantics of this one is S0. S0 union with S2, S0, S2. I started with S0 and S2. I ended up with S0 and S2. So that's fine. That's the fixed point. So I calculated the semantics of new x, A false, or true x, right? And this turns out to be S0 and S2. Does that satisfy our intuition? It does, right? We were seeking states from which I could do something and end up in a state that cannot do any A, namely S2. And those are namely S0 and S2. So minimal fixed point is what we are seeking here. Right? To give you an intuition why minimal fixed point is what we are seeking, minimal fixed point intuitively stands for iterating only finite number of times over your fixed point construction. So it's like a loop that can loop only finite number of times. You can only use this iteration going to x and then coming back to the same formula a finite number of times. You should eventually satisfy the rest, right? So you can avoid this only a finite number of times, but eventually you should reach a state which satisfies this one, okay? And that's a typical reachability property. You want to say, no matter how I evolve, in a finite number of steps, I reach a state in which the formula is satisfied. Typically, those formulae are specified using minimal fixed point, when you require the iteration to happen only a finite number of times. However, safety formulae, where you want to say, no matter how many steps I take, I end up in that property, they may require an unbounded, infinite number of iterations, and then you specify them using maximal fixed point, right? So if you want to iterate finite number of times, then you use minimal fixed point, because you want to reach somewhere after a finite number of steps. If you want to iterate potentially an infinite number of times or an unbounded number of times, then you use maximal fixed point. And in particular, if you look at this formula that was not intuitive, it was not intuitive because it allowed us to loop infinitely often here without satisfying this one. In particular, if we were here, we could spend our life here without doing anything useful and never reach there, but still maximal fixed point was satisfied. So you could iterate on in the fixed point construction infinitely often, right? Is this clear? Yes.
How can we be sure that the fixed points have a least fixed point?
Well, it is guaranteed. It is guaranteed that if you satisfy this syntactic constraint, you always have a solution. You always have a minimal solution.
The formula is the fixed point?
Yeah. So there is a fixed point theorem that makes sure that exists always. Yeah, sure. That's a very good question. And the same for maximal. So these two solutions are unique and exist if you satisfy those syntactic constraints. Yeah. Good. So I have more examples, but I think I will leave them given the time. So I have, this is the calculation. You can look it up later. This is another example using the same formula. I will. Okay, so if I want to say there is an infinite path along which an A transition is always possible, then what should I use typically? Minimal or maximal fixed point? Just according to your intuition?
Maximal.
Typical, it should be maximal fixed point. Look it up and see how the calculation goes, but and you see that the maximal is the right one for this particular example. Okay, so two patterns that I want to tell you about, and then I'll stop here. One is safety. So if you want to specify a safety formula, saying that for some execution, phi holds everywhere. There is a dual which says for all executions. I can write it down on the board for you. For some execution, so there is at least one path in your execution, right? So it corresponds to the CTL that starts with E, right? For some execution, phi holds everywhere. It's specified like this. No matter how you evolve, even infinitely often, right? You satisfy phi right now, and first of all, you cannot deadlock, and you can go on back to x such that phi is satisfied again, right? So there is some infinite path, right? When I say execution, I mean an infinite path, in which phi is satisfied everywhere, no matter how you evolve. You cannot deadlock, so the path should not end, and also it's possible to extend that path and go back to x, whereby phi is satisfied again. How do I modify this to an A formula so that for all paths this is satisfied? So if I want to say that phi holds everywhere no matter how you evolve, if I want to say for all executions phi hold everywhere, so A, G, phi basically in LTR or CTL. Yeah, so the first thing we should do is to replace this diamond here with a box, right? No matter how you evolve. So I should not require a single execution, but in all executions, in all possible actions, the target should satisfy x. I could also remove this because I don't care whether the system deadlocks or not, right? So I say phi holds now, and no matter how I evolve, I go back to x. That's AG phi, basically, in CTL, LTL term. Yeah? Everyone agrees? Another property? Eventually phi will hold in the future. That you already saw in this example. So I say phi holds now, either phi holds right now, or you can do something, and no matter how you evolve, you go back to x. And you can only do this finite number of times, so eventually in all possible paths, you reach a state in which phi holds. Right? You should be able to do something, and no matter how you evolve, you end up in a state which satisfies x. Because this can iterate only a finite number of times, then you eventually reach a state in which phi does hold. So you cannot avoid reaching a state in which phi holds. You remember yesterday we tried to specify this using regular expressions and we failed. So regular expressions are not capable of specifying such properties. Well, I see you're all very puzzled about this formula. So if you don't have that, you could deadlock. If you deadlock, so suppose we don't have this, okay? If you deadlock, this is true, right? This is saying if you can evolve if you can do something, then you should satisfy x afterwards, right? No matter how you do something, x should be satisfied. If you cannot do anything, then there is nothing to check. This is true, right? Then the whole formula becomes true. So in particular for the, who loved the trivial transition system? You? Right? So for the trivial transition system without any transition, this formula without this would be true, right? So the closest formula that you could specify using a regular expression, and I saw this mistake also 2 months ago. I was at a presentation of a very well-established scientist, and he wrote this formula instead for this property. He wrote something like this. I don't remember the exact formula, but true star, phi. So no matter how you evolve, there is always a path to phi. This is much weaker property than this one, right? In particular, you could avoid doing satisfying phi by keeping on doing other things. So suppose you have some A transition, and phi here means doing a B. You could always avoid doing a B by doing an infinite number of A's in this formula. But in that formula, you cannot do this because minimal fixed point requires you to eventually reach a state in which phi is satisfied, actually. Right? Is this clear? Good. I think this is a good point to stop. Data, right. I promised to talk about data. So, Oh, I can do it. That's not a problem. So suppose I want to specify, I have an ice cream machine. That's my favorite example. So suppose I have an ice cream machine that can produce ice creams and can be refilled. Okay? And so I have two actions at the interface, ice cream and refill. I need my sponge here. Sure.
I have a question about last one.
Yeah, sure.
Why we need something like an equation for describing these intuitions? Another syntactic structure would be more simple and direct.
I think it's a difficult question. I mean, you should give me an alternative and I can tell you whether it's capable, it's expressive enough for this purpose or not, right? If you don't give me an alternative and you say there should be another simpler solution, I cannot give you an answer to this question. It's too vague. There is so much out there that I cannot tell you, okay, there is nothing else that can satisfy this.
Like universal and existential symbolic signs in
So there are extensions of CTL star, for example, that so there is also there are three logics, for example, based on CTL star, which may be able to specify some of these properties. But as I said, it's a difficult question because you should give me an example of a logic. I will give you an example of a formula that cannot be specified in that logic. This is more expressive, right? Otherwise, if we keep on talking about different logic and say, okay, if we extend it to this, then that might work. I don't have a concrete answer. Maybe you have some?
Maybe. One of the things is that quite a lot of people that are confronted with modal new calculus, and I was among them, basically say, I don't like this. This is too complex. It should be simpler. I actually that there are all kinds of intrinsic problems with this alternative logic, and that ultimately, after I really started to understand, I still make mistakes with this, the new calculus was completely superior to the alternative. And this repeated itself a few times again. Ultimately, this notation works quite well. And therefore, I at some point gave up and said, this is it, because this is apparently such a good logic. Well, I know one example that I cannot specify, but that is a very fabricated example, and for the rest, it always works. So, I stick to it.
So,
You can imagine that you go to, say, fundamental higher order logics in which you express these fixed point combinations. In most other, say, plain logics, such fixed points cannot that easily expressed. Well, there might be in that context something that is actually better, but I don't think that it is known yet.
so I agree with both of you that model mu calculus may seem difficult for engineers, right? The way to circumvent that is to come up with these patterns and then give them a name for engineers. So if someone wants to specify safety property, rather than writing mu and nu, they just write safe something, and then the tool will translate into the right one. That's one way to go. But there is a more fundamental problem. Most engineers find, in general, thinking about time very difficult. So there is a lot of experiments in different contexts that no matter what logic you give to the engineers, they find writing temporal formulae intrinsically difficult, right? Maybe it's a problem of training, maybe it's a problem of human brain, I don't know. But for example, big companies like Synopsys, hardware companies, they built into their tools the possibility of specifying typically linear temporal logic formulae. And they found out that they're rarely used by engineers, although they're very powerful tools, much more powerful than assertions and many other things that are commonly used. People tend to find thinking about time quite difficult, no matter what tool you give them. But to avoid using fixed points, I think one way to go about is to give these patterns, and this is very common practice in industry. So there are many domain-specific temporal logic languages, temporal logic-based languages that replace difficult constructions with some shorthands that people can use and do without these fixed points, right? The power of the logic is useful mostly for people who have a better understanding of the math behind it, but for people who don't understand it, you may use simpler shorthands. That might be an answer also. I don't know whether you have anything. Okay, so let's go back to this ice cream machine. So I am very bad in drawing, but you have seen these ice cream machines where you could get an ice cream out, right? And you can refill them, right? And I want to specify that this ice cream machine should be able to produce an ice cream after each should be able to produce 10 ice creams, or let's start with 2. 2 ice creams after each refill. So let me write it down. The machine should be able to produce 2 ice creams after each refill. The machine should not So 2 properties. One is that it should be able to produce 2 ice creams in a row without a refill in between. So after you do 1 refill, it should be able to produce at least 2 ice creams. And another property, it should not be able to produce 3 ice creams without a refill in between. Right? So when it's empty, it should not produce less ice cream and give you some not insufficient ice cream or not good quality ice cream, basically, right? How do we specify the first one in Hess-de logic or model mu calculus? You can use regular expressions, you can use fixed points, whatever you want. Any suggestions? Yes?
Box, refill, diamond produce,
Let's call it ice. I wrote ice here, okay. Diamond ice, and then
diamond
another diamond ice, okay. Okay, it's not bad. I don't want to argue much about it. It could be improved, right? But this is a good start. It says initially if you refill it, it will be able to produce 2 ice creams in a row. Okay, it can avoid that. It can maybe do some other things, right? That part could be improved, right? So you could strengthen this part by specifying that it cannot do anything else but producing ice cream if you want, right? But another point that I think should be improved, this only talks about the initial refill. It doesn't talk about other refills that happen in the future. How can I improve that? So you understand the problem? There are 2 problems with this formula. First of all, it says it can refill, it can produce 2 ice creams. It doesn't say it should, right? Secondly, it only talks about the initial refill and not about subsequent refills that happen in the future. How do I improve this second problem? That's more fundamental, yeah?
with fixed points.
You could do it with fixed point, or you could do it even in regular expressions, right? You could write true star, right? So you could write here true star refill. So no matter where you end up, if you do a refill, then you can produce 2 ice creams, right? Everyone agrees? Good. How about the second one? Okay. Okay, I'll write it down. So you're saying ice, ice, ice. Not this, right? So suppose my machine has also some other possible actions. It can, whatever, make a noise, for example. It can turn on a light, right? And I do ice, light, ice, light, ice. Then this formula is satisfied. I'm not doing 3 ices in a row, right? But I do something in between. How do I avoid that problem? You understand the problem with this formula? It says you cannot do 3 ice creams in a row, but you may be able to do something, some irrelevant thing in between, and then through indeed 3 ice creams in a row by doing that irrelevant stuff.
Can put box refill bar between the diamonds.
It's getting complicated. So let me rewrite this first. This is good, but we could rewrite it in a simpler formula. Where did I put my sponge? There. So not diamond, ice, 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 true. It can be rewritten as what? Box, ice, ice, ice. And then false, right? This is saying no matter where you evolve, if you do 3 ices in a row, then you end up in false. That's the same formula as you just suggested. So now I think this is easier to fix. How should we fix it? Very good. So if we put here not refill bar, that's what you wanted to say, right? Ice, not refill bar, ice. And then it doesn't matter whether you put not refill bar or not here. That doesn't matter. If you do 3 ices in a row with anything but a refill in between, then you end up in false. Right? So you can never produce 3 ice creams without having refilled in between. Right? Now, suppose everyone agrees with this? Everyone is okay? Suppose I change my formula to 200. And here 201. Then, of course, I have to add 198 of these ices and refills afterwards, right? It soon becomes not practical to specify these things using this recipe. The recipe that does work is using data. So you could say, I have an ice cream machine, so let's call this M for machine. It has a variable that shows the current capacity of the machine, current content of the machine, how many ice cream it can produce right now. And initially, it's for example, initialized with 2 or 200 or 2,000, whatever you want. If I do an ice, then I end up with one less. You could also specify if n is greater than 1, then if I produce an ice, then I end up with 1 less, right? No matter how I do an ice, I end up in the same formula with 1. I should write a minimal or maximal fixed point here. I haven't written it down. Okay. So if I can produce an ice cream and I do that, then I end up with 1 less. If I do a refill, if I do a refill, I end up with, what should I write there? How does the capacity of the machine, how does the content of the machine increase? So it becomes M of, say, 200. If every time we refill, we add 200 ice creams to the machine, right? And n is always, for example, greater than 0. So you can never go below 0. That's what we wanted to specify. You can never produce, for example, 201 ice creams in a row. And if n is greater than 1, then it should be possible to do an ice cream. Or if you want to strengthen this, you can say you should be able to do an ice cream and nothing else if you want. I wrote here, n is greater than 1, then diamond ice cream true. Greater than 0, yes, you're right, perfect. Yeah, greater than or equal to 0 or greater than or equal to 1 or greater than 0. Yeah. So this way, using these parameterized formulae, I wrote x here, I meant m. You can add data to your formulae and count, or you can, for example, add list here and implement push-down formulae. So you can push something on the stack or at the end of the list, and you can pop it up later. So you can specify very, very expressive types of formulae that could not be specified using many other logics around. Okay? And in this case, because I want to iterate as many times as possible, this is a maximal fixed point. So in MCL2 syntax, this would be new m dot new m dot, and I forgot how I think you write it like this, n of type nat equals to 200 dot, something like this. Is that the MCL2 syntax for initializing the formula?
I think it is an is. In the back of there's an appendix with the precise syntax of all the formulas.
It doesn't matter what the exact.
I always have to look at
Yeah, anyway, but here you specify the formula and then you see what the initial value of n is, okay? And what the exact syntax here is equal or something else, I don't remember. But these type of formulae allow you to specify very expressive things like counting, like pushing on a stack, popping from a stack, adding to a queue, which is not possible in many other logics. And this gives you a lot of succinctness power. So you can very succinctly, for example, code LTL, CTL, these type of formulae if you use data. That's something you showed in a paper some years ago. 2 questions, yes. Here, the last one. So first of all, I want to say you can never take more ice creams than the capacity of the machine, right? So you cannot go, maybe n is not a good, maybe integer is a better here. So maybe z is a better type here because that allows you to go below 0, right? So I'm saying if you do an ice cream, you go 1 less, right? And I could potentially even remove this. I could say you always, if you produce an ice cream, you go 1 less. And you can never go below 0, thereby you can never produce more ice creams than in capacity, right? That will correspond to this property, basically. You can also write first order logic. You can write there exists for all. I think verification will become more and more difficult, especially if you use unbounded types here, then you should forget about verifying. But yeah, you can potentially. Yes?
Is in the parameterized set of states?
So the initial fixed point equation stands for a parameterized, so it is, you can see it as an infinite number of equations, but you start with an initial number, right? So you start with 200, right? So then thereby you pick one of them as your starting point to verify. Yeah. More questions? If there are no more questions, well, this is officially the coffee break time, but we could go on for another 15, 20 minutes.
What shall we do?
Are you tired? No? Yes? Yes? No? So let's take 15 minutes break and then come back. Yeah? So we come back at 1:45 and then Jan Friese will take over.